Okay, so now I think we've hit into the thermodynamics section and the ideal gas law section, which I'm pretty sure all the chemistry majors will know a lot about, the PV equals nRT. So we'll start out with that. And this is problem number 18.61. And I'll let everyone read it real quick, and then yeah, tell me what you guys think on how you should solve it. All right. Any ideas so far? Well, I know for one, we're going to use the ideal gas law, so we're going to use PV equals nRT. And is everyone familiar with the variables in this ideal gas law? Okay. So P is for pressure, of course. V is for volume. N is the number of, I think, molecules or atoms. Can someone help me out there?
Moles.
Moles. Okay. Molecules. And then R is the constant. I forgot the name of it. Starts with R, of course. And then T is for temperature. So we're given that temperature 1, the starting temperature of this tire, it is 5 degrees Celsius. And the end temperature is 45 degrees Celsius. So what I'm going to do now is put T1 equal to 278 Kelvin. And to get that conversion, you do 5 degrees Celsius plus 273.15. And that will give you 278. The final temperature of the tire is 45 degrees Celsius. And in Kelvin, that is 318 Kelvin equals 45 degrees Celsius plus 273.15 here. All right. So now that I got my final temperature and initial temperature set up, I'm going to get my initial pressure. So what do people think the initial pressure is? It's kind of tricky. It's kind of a curveball, but what do y'all think? So zoom out a little bit and show you the question.
It should be the absolute pressure, which is atmospheric plus gauge.
Excellent. Nice. Yeah. So I actually messed up when I did this because I didn't use the absolute pressure like you said, Thomas. So yeah, good job. Yeah, so the pressure, we're going to need the pressure of the gauge. I wish I had that with me, but it's when you stick it into your tire and then that little thing pops out and, you know, the pressure. But we need the atmospheric pressure added onto the gauge pressure as well, as Thomas said. So we'll use 1.2. That's the atmospheric pressure, ATM. And I think, yeah, we're given the 1.7 atmospheric pressure of the gauge. So we need to add that together. And I'll put in parentheses, that's absolute. All right. And that equals 2.72 atmospheric pressure. So that's our starting pressure. So that was the trickiest part, to be honest. And then from here, I'm pretty sure everyone has the math skills to get the answer. But let's go through it. Just to make sure. So now we want to get the final pressure. So I'm going to go PV over T equals NR. And assuming the tire is closed with the cap thing, this will equal a constant, the N times the R. So the number of moles stays constant in the tire. So now I'm going to set up pressure 1, V1, over temperature 1 should equal your final pressure, your final volume, and your final temperature. And we want the final pressures, so we're going to isolate P2. P2 equals P1, just some algebra. P1, P2, T1, oops, that's T2, should be T2, T1. And plugging in the numbers, you should get about 2.94 atmosphere. Now, remember what Cassie said Thomas said in the beginning. This pressure that we have, the 2.94, that's the absolute pressure. So that's the atmospheric plus the gauge. So we need to subtract the atmospheric pressure, the original atmospheric pressure, from this P2. If that makes sense. And yeah, stop me at any time. So now the gauge pressure is, I'll put PG. It's going to be P2, which we just found to be 2.94 atmospheres, minus your, I'll just put 1.02. I don't know how to label it right now. That should give you 1.92 atmospheres. And this is your gauge pressure. All right. Did that make sense to everybody? And can you hear me with my mask on? That's kind of okay. So I'll give everyone a moment to write this down or adjust it a little bit. We'll set up the next problem. This is a fun one. Just didn't add it today. Okay, so I think the chemistry majors will like this one. Oh, I liked it. So I'll give everyone a minute to read this. Yeah. All right. So what can anyone tell me about the system's temperature in general? I'm not sure how to ask it to lead you guys to the question. So, assuming there's ice remaining. It's okay to guess and be wrong. Maybe I'm asking a bad question. So what's the final temperature of the ice?
0 degrees Celsius.
Bingo. That's what I was looking for. So that's a good known, because it says how much ice melts in the cooling of the enzyme sample. So we know the final temperature is going to equal 0.0 degrees Celsius. And so let's set it up. So does anybody know what the heat of fusion constant is for water and the definition of it as well? So let's start with the heat of fusion constant. That's okay. So the heat of fusion constant is, so I'll write the definition here. It's the amount needed to change 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of water at 0 degrees Celsius. Oh, this is important too. At normal ATM or atmospheric pressure. Yeah. So the heat diffusion constant is important. I'm pretty sure Professor Rudy is going to throw in a phase change of water problem. Yeah, they always get so tricky in thermodynamics. Like for example, they'll probably say, if you make a cup of coffee and put an ice cube in it and put it in the fridge, what's going to happen? Something like that. I had that question before. I forgot the exact question in my undergrad, but so definitely practice these phase change problems with water. It's going to help you a lot. I'll say that. Okay. Oh, so now let me write out the actual value for the heat diffusion constant. It's 3.34 times 10 to the 5 joules per kilogram. And I'll put here for water. So this is a protein. Okay. And we're going to need two equations. So two heat equations. Does anybody know those equations? There's going to be one for water and one for the temperature change of the system, mainly the bio. Okay, I can start you out with the water one. So I'll write it in blue so everyone knows. So heat. So the melting phase of water, which is denoted by Q, is the mass of the water times the heat diffusion constant. And the vial, I'll write that in gray. So the vial will be the mass times the specific heat, which is given, and the change in temperature. Okay, is everything good so far? I'll give people a minute to write this down. And I'll put these notes up online. So yeah, don't feel pressure to get everything in at the moment. Oh, let me write. Change. Put melt phase. More specific, melt phase transition. Okay. So now this is the important part, the setup. If you get the setup right, you're gonna get most of the points, I feel. So what we want to find out is the net heat of the system. So net Q, put that for now. And I'll put sample, vial, and ice. And let's not forget our goal of the problem. So we want to find how much ice melts in the cooling of the enzyme. So basically, we're looking for how much water melts, so the mass. We're going to have to isolate M at the end of the day, the mass of the water. Okay, so let's write out the Q. Put sample. So can anybody tell me what equation we would use for that? Okay, so maybe I should show the equation of the problem I need. Oh shoot, I just noticed something. So this QMCT, this is actually the temperature change of the vial. I switched them around. And this is the transition for the water. Okay. Okay. So for the sample, we're going to use this guy, Q times the mass. Well, Q equals the mass times specific heat times the temperature change. So let's write that out explicitly. So we're going to have Q. I'll denote it with Q subscript S equals mass of the sample times the specific heat of the sample times the temperature change of the sample. And plugging in our values, we'll get 16 grams, or put it 16 times 10 to the negative 3 kilograms, just to put it in SI units, times the specific heat, which is given. Oh, shoot. Okay. And times the temperature, negative 19.5 degrees Celsius. And you might be wondering, like, hey, there's Kelvin here, but you're using Celsius. As long as you're consistent in this case, it should be fine. Because if I convert this 19.5 degrees into Kelvin, I'm just going to do the same thing for our final temperature. So basically what I'm saying is we're going to have another temperature we deal with in the other equation. And as long as you convert both of them the same, you're going to get the same answer. You'll probably see later what I mean. And you can always check it by converting 19.5 to Kelvin, and you will get the same answer. So I check that. Okay, and then this should equal negative 328 joules. Oh, no, I'm looking too far ahead. Negative 702 joules. So basically, this is how much, how much heat is lost or transferred from hot to cold when the sample is being cooled down. So this sample is losing energy. All right, so let's write down the heat of the vial. So does anybody know what equation we would use for this guy?
Transition equation.
Are you talking about the one with specific heat, Thomas?
Oh, vial, yeah. So this temp change one, sorry.
Oh, it's okay. Yeah. Okay. Yep. So Thomas is right. We use the Q equals MCT. So Q. Now I'll put MV, QV. So you all know it's for vial. Specific heat of the vial times the temperature of the vial. Plugging in our numbers. So the vial weighs 6 grams. Put this in SI units. Specific heat of the vial is given. And 19.5. Yes, yeah. Did I? Just make sure I didn't make a mistake. Oh, yeah, because they both start at room temperature, the vial and the sample. So that's why I was talking about you can leave them in Celsius, or you can convert them to Kelvin if you want. That's extra work, but to be safe, I would convert them to Kelvin personally. Okay, and then this. Oh yeah, what's up?
Temperature here, isn't it the same for Kelvin and Celsius?
Yeah. So that's what I was trying to say. I just didn't know how to say it. So yeah, you said it better than me. Thank you. Yeah, exactly. Okay. So negative 300. So this equals negative 328 joules for the vial. So the vial loses 320 joules of energy. Now the final piece of the puzzle is for the ice that melts. Now, what equation do we use for this? Okay, we use the mass times the heat of fusion constant. And yeah, from there, let's just set up the whole equation. So this is similar to your 12-10 days, the principle of superposition, but this time with heat. We're adding heat together. So write it in this color. So we're going to have the heat of the water. I'll just put the numbers in. So minus 702 joules. And that was the heat of the sample. And minus 328 joules. And that was the heat lost by the body. Yeah. Okay. And then I'll put a side note here. So when you isolate M, this yields mass of H2O. And we're talking about this M here. And I'm confident in everybody's algebraic abilities. I'll just write down the answer and you could practice in your free time. Or all right. So that was a little long-winded, but did the process make sense at least? Okay, I'll give everyone a minute to think about it real quick. So I almost guarantee you there's gonna be a problem like this on the exam. Actually, I do guarantee you. When I TA'd for Dr. Dale last in spring 2019, yeah, dang, time flies. He had a problem like this on his exam, so chances are you're gonna have a problem like this since Rudy is making me do it in discussions. Is there any mechanical engineers in the building? Rep mechanical engineers.
Yep.
Nice. Okay, so this problem's for you. Where is it? Yeah. What's this one? Yeah, this is the one. There you go. I'll let everyone read it real quick. Oh, and before, so let me show you my shirt. So when all y'all graduate, just know your success, it's not an accident. Y'all worked for it. So just remember that. It's not a fluke when y'all walk the stage. Okay. So does anybody have an idea how to tackle 17th of June? So there are equations. If you weren't introduced to this yet, you won't know it. So has Rudy went over thermal expansion? So, okay. So I'll write the equations, but then if I do that, it's just gonna, well, it won't hurt. So your change of length, if there's heat, is gonna be this constant. I forgot what it's called. It's a constant, something coefficient, times your original length, times your delta T. You change the temperature. And basically what this equation is saying is your change in length is dependent on this coefficient and your temperature change. So you could predict, which is what mechanical engineers do when they build bridges. For example, the Golden Gate Bridge, I'm from California, from the Bay Area. When I drive over the Golden Gate or any bridge in the Bay Area, there's always like two metal plates, and there's like a gap in between them, and they're trying to account for the expansion of the metal when it's summer. Because if you don't, if you just make it flush, during the summer, the metal's gonna expand and you're gonna get bad things to happen. So that's why you need to account for this. Okay. Yeah, so that's the only equation we need. But let's draw the free body diagram. So this is a wire at 20.0 degrees Celsius. And situation 2. Now the wire is at 420.0 degrees Celsius. That's quite a difference in temperature. A little longer. So it was 1.5 meters. And it says it changes by 1.9 centimeters. So not too much, but it can make a big difference. And from here, yeah, so they asked to compute its coefficient. Yeah. Oh, so this is the coefficient of linear expansion. I should have just read it. So that's what we need to isolate. And doing that, we get alpha equals delta L. So now it's just algebra. L naught delta T. So let me plug in the values explicitly. 1.9 times 10 to the negative 2 meters. 1.50 meters. Times your temperature change. So final minus initial in this case. So 420 degrees Celsius minus 20 degrees Celsius. And you should get the coefficient of linear expansion is 3.2 times 10 to the negative 5 inverse degrees Celsius. Okay. Does that make sense? Yes. Okay. So this may seem like a small thing right now, but for the mechanical engineers out there, I don't know if you'll run into this because I'm not a mechanical engineer, but it's nice to know if your boss ever asks you, like, hey, what's the coefficient of linear expansion for this type of steel? At least you know how to, like, at least you know the concept of it, right? So it's good. Okay, that's good. Oh, so this one's a fun one to me. Kind of a weird one, actually. Okay, so oh, I did. Okay, so we're going to do 17.72. And does anybody know what black body radiation is? Okay, so black body radiation is like based off this concept where you have an object and it absorbs everything. It doesn't radiate any type of electromagnetic radiation. So every object radiates some form of electromagnetic radiation, but there are objects that don't. Well, very close. Like I think graphite has a emissivity of 0.09 something. So that means it's very close. It doesn't radiate much at all. A perfect black body, E would equal 1, so it doesn't radiate. And you'll see that. So for part A, what is the rate of energy radiation per unit area of a black body at a temperature of 273 Kelvin and 2,730 Kelvin? So part A. Any ideas? Oh, has Professor Rudy went over this? Dang, okay, so I have to give you all the equation. Okay, so the equation for, how do I say this? Heat current. Well, to get power, well, let me just write it out, and then I could say it better. So H is your heat current divided by your area. That's going to equal your emissivity. It's not your exponential function. It's like a constant as well for different objects or materials. And sigma, which is your Stefan-Boltzmann constant. Is that familiar to the chemistry majors? A little bit? Okay, cool. And then also the temperature to the fourth power. So what this left-hand side describes is the power output, right? Amount of power per area. Okay, and I like to make it analogous to pressure. Does anybody know the definition of pressure in classical mechanics? Oh, it's like a force per area. So if you have like a needle poking down in your skin, it's going to have a very large pressure because the area the needle's hitting is very small. So if you have a big number divided by a fraction, you get an even bigger number. Anyways, that's what I like to think of this, is like the amount of current per area. Yeah, and from here, now it's algebra or plug and chug, unfortunately. So the emissivity, yeah, so it says black body. So theoretically, the black body emissivity is 1. So it doesn't radiate any type of electromagnetic radiation. Times your Stefan Boltzmann constant. I did not memorize it, so I have to write it down. And times 273 Kelvin. And this is going to equal 315 watts per square. Okay. So that was for 273 Kelvin. For part B, same thing. But we want it for 2,773 Kelvin. So now H over A. Black body, so emissivity is 1. Same thing, Stefan Boltzmann constant. And this time 2,730 Kelvin. And that's going to equal 3.15 times 10 to the 6 watts per meter squared. All right, so as you can see, well, I didn't think about it too hard, but if you increase the temperature by a factor, by a magnitude of just 1, so this one's 2 times 10 to the, so if you just increase it by a factor of magnitude of 1, this goes up. So basically the power output changes, or the amount of radiation changes quite drastically based on the temperature. So any questions on this? I know it wasn't too exciting of a problem. Support to them. Okay. Okay, so we have a Young's modulus question. I think that's the last one. Oh shoot, my brain is scrambled. So 17.23 had another one. So we have to go back. Yeah, this guy. There's a part B to this one. So for part B of this question, the wire is stretched just taut, 0 tension at 420 degrees Celsius. Find the stress in the wire if it is cooled to 20 degrees Celsius without being allowed to contract. And Young's modulus for the wire is that value. So can anyone describe the situation you're trying to tell us about in your own words? So basically, the way I'm thinking of it is like, if I had a rubber band and it's at a certain temperature and I were to cool it, how much force would I feel in between my hands, right? If it was being cooled down magically somehow. So it would like go like this. But in reality, I'm holding it. But if you were to cool it, it's gonna contract. So like how much strain, stress is going to be caused if you were to cool it? Okay, and again, this one is, it is plug and chug, unfortunately. And if Rudy didn't give you the equation, I have to give it to you. That's no fun. So force times the area, thermal stress equation right here, kind of similar to pressure. Well, it's not pressure, so I don't want to say that. Times your coefficient of linear expansion, times your delta T. And from here, Yeah, no fun. Plug and choke. Let me write it out just be complete. Why did I do that? So as you notice, our temperature is different this time. We went from, yes, so we went from our final temperature. Yeah, so it's at 420 degrees Celsius and you're cooling it. So we did 20 minus 420 degrees Celsius. That makes sense. Stop me at any time if you have questions. And this should equal 2.6 times 10 to the 9th pascals, which is a unit of pressure, by the way. Okay. Any questions on this? Okay, cool. Dang, I went through that too fast. I was hoping I would have more questions. So that's it for this one. Any questions before I let y'all go? It could be about anything. Okay, cool. See y'all next week, and yeah, study hard, keep the spirits up as usual. Feel free to email me if you ever want to do office hours. Yeah, take care.
Yep. Thank you. Have a
Yep.
good day.
You too.
Yep.